Okay, so we saw that if you define T as a transformation T to R3, T from R3 to R3, defined by this matrix, its kernel is the span of this set consisting of a single vector. In R3, that set is identified is a set of multiples of (1, -1, 1), because it's a set of T times 1, -1, 1. Now, from multivariable calculus, you see that that's a parameterization of a straight line. Okay? And that straight line is a line in the direction of this vector. You make a unit vector out of that. You do all the things that you do in multivariable calculus, where you're actually talking about these things in R3. Okay, so it's a line in R3. So well, actually, I haven't gotten to that yet. I'm trying to get ahead of myself. I was going to say T collapses the space. What's a set of vectors? It's too many words. I didn't want to use the term, but it's a term everybody should understand. The question I want to pose is, what is the range of T? Well, the range is a set of vectors you get over in this R3. How do we get a handle on the range? Well, I'm going to do it this way, and there are other ways to do it. Multiply this out. Okay, this equals this. But another way to say what that equals is A1 multiplied by 213 plus A2 multiplied by 123 plus A3 multiplied by -110. If you just look here, you got your 2A1 here, and your 1A2 here, and your -1A3 here. So if you continue to write this out as, you know, 2A1, A1, 3A1, 2A2, A2, 2A2, 3A2, negative A3, A3, and then add them up, you'd see that you came back to this. And what this shows you is, where do you see 2, 1, 3 in this matrix? It's the first column. Okay, so here's your first column. That's your 2, 1, 3. Your second column, and I'll just go ahead and do these in colors. Hope nobody's colorblind, but you get the idea anyway. Okay, so the vector product can be written as A1 times the first column plus A2 times the second column plus A3 times the third column. I'm cutting corners a little bit for the sake of time. And this is, of course, something that your assignments are going to draw out anyway. So you kind of have to discover a little bit of this yourself. Because this matrix reduces to matrix of rank 2, and you've seen what rank is. Okay, so you reduce the matrix, and the matrix has rank 2 because you have 2 columns of non-zero vectors when you finish the reduction process. Making a lot of statements that I decide to change. Say it more compactly. A has rank 2. See its reduction. It follows that the span of its columns has dimension 2. So if you're looking at all the vectors in R3 over here, and all vectors over here in this R3, they say all the vectors in R3 map to subspace of R3. The subspace has dimension 2. this subspace is a plane at R3 through the origin. The dimension, and I'm just asserting this, if something needs to be proved, okay, for any V vector spaces V and W and transformation from V to W, the dimension of the subspace in W that's spanned by the images of all the vectors in V. And what I mean by images is, well, I'll draw a picture in a minute, but it's just all the vectors you get over there when you map all the vectors over here. Okay? Every vector over here has an image over here. But as we see from this example, not every vector over there is the image of something over here. In this example, the images of all the vectors in R3 under this transformation from this matrix A lie on a plane in R3. Okay, well that's not even, the plane has zero volume in all of R3. Almost none of the vectors in R3 are on that plane. It's kind of a big deal. Okay, well, dimensions of the subspace of W spanned by the images of all the vectors in V is equal to the rank of the transformation matrix A. Now there's a lot in that statement. I haven't proven, I've only asserted that every linear transformation can be represented with respect to some pair of bases by a matrix A. But it's so. Okay, so this is a big deal. And an even bigger deal is another big principle. All the rows of A yeah, I think I said it wrong. It says rows. All the columns of A are images under the transformation. Picture this, and I'll tell you why it's so. Here you got V, Here you got W. Here you have within W the image of V. The set of all vectors that map from V into W have to be in this image. Now the image might be all of W, and when you think of an image, well, think of this. The image could be as big as V. Okay, so if V is R2 and W is R3, then R2 can't map into anything of higher dimension than R2. And yeah, I don't want to go on with that statement just yet. Okay, if V is R2, it's a plane. If W is R3, V can't map into anything bigger than a plane. So it leaves most of R3 empty. Now, it's also possible that V is R3 and W is R3, and as you have it here, V maps onto a smaller subspace. V is three-dimensional, but it maps onto a two-dimensional subspace. So the image of V doesn't have to be the same size as V. It doesn't have to have the same dimension as V. If you think of an analogy, if I'm walking outside on a sunny day, I cast a shadow. I'm three-dimensional most days. My shadow is always two-dimensional. Okay? So the image that's created by my shadow is of less dimension than my body. Okay? Okay, so I'm trying to summarize a lot of stuff here, and mostly by analogy, but I've asserted that all the columns of A are images under the transformation. Why is this? Well, let's just go back to the example. Okay, now I've just rewritten this. A1, A2, and A3 are the components of some vector in V. They could be any numbers. They could all be 0. But, for example, you could have A1 equal to 1, A2 equal to 0, and A3 equal to 0. So if A1 is 1, A2 is 2, A3 is 0, then AV would be just 2, 1, 3. 1 times 2, 1, 3, and the rest of them are zeros. So 2, 1, 3 is certainly in the image. More specifically, A times A times 1, 0, 0 is 2, 1, 3. If A2 is 1 and the other two are 0, then you conclude that A times 0, 1, 0 equals 1, 2, 3. Well, here's your first column, here's your second column, and then let A3 be 1 and the other two be 0. You'd have A times 0, 0, 1, and that would equal your third column. That could have been said a little more simply, but it's pretty simple to see if you look at the vector that this is going to be the case. So there we have the three columns explicitly written as the sum, as a transformation of a vector in the first R3. Okay, so there we have it. You can also prove that these three vectors span all of the image and that they're not linearly independent. Because if you add this one and this one, sorry, subtract this one from this one, you get this one, okay? Yeah. This one minus this one equals this one. They're not linearly independent. Okay, all this stuff is related in a way that we don't have time to get to today. But what I've tried to give you is kind of an overview of the big deal here, which is this. And I'm going to say it not as generally as I could because I haven't developed all the terminology. Hasn't been proven, but here's the big deal. Rank of A plus the dimension of the kernel is the dimension of your V space, the space you're mapping from. In the dimension of the image of V, you said something that's probably because I'm writing down off the board. Am I right?
Yes, sir.
Okay, good. This is a big important thing, so it's a good thing that you got me to do that. Okay, dimension of the image of V is the rank of A. So you put that together into these abstract pictures of transformations and gain a pretty good overview of where you're going. So as you work through the next couple assignments, hopefully this will help you pull things together and give you a framework for understanding the details that you're going to see through the WebAssign. Okay? I'm going to turn the camera off and I'll be right back.